Right, I think the recording has started.
Yes, sir.
Yes, it is showing that recording has started. All right, so I believe that you can see the screen and we will therefore start the class. All right.
Yes, sir.
Okay. So this is what we did in the previous class. I'm just continuing from there. And we had, if you remember, written down a series of 7 or 8 reactions, different types of reactions. And there we basically said that that if you can uh, pick up the pen, what happened? Pen is not working. 1 minute. Give me a minute. Let's sort this out. Right click. It is saying pen mode. Okay, okay. I think this now I've got the pen mode. Yes. Okay. So what was I saying? All right. So we had talked about around 7 or 8 example reactions. We had written down the reaction equations, and from that reaction equations, we tried to illustrate the rate laws that we would get. We basically arrived at the conclusion that if we can write the rate, if we can write the rate law in this kind of format, y and so something, some exponent x, y, z. All right. So if we can write it in this format where A, B are the reactants and D could be a product or something, but basically it follows that notation that we established in the first lecture. Remember that so you have A plus B gives C plus D, and obviously these are the respective stoichiometric coefficient nu A, nu B, nu C, and nu D, right? So we were saying that if we can raise this to some power and we can write the rate law in this manner, then we can talk about the order of the reaction. And we can also talk about the partial order. Partial order means that order with respect to a particular reactant, right? Particular reactant like this. Okay, so order with respect to A is X, order with respect to B is Y, order with respect to D is Z, like that. Okay. Now we where is the the presentation crashed, right?
But your screen is not visible.
The presentation has crashed. 1 minute, give me a minute. I have to stop the recording as well, I think. Presentation has crashed. This is something that I face not frequently. Okay, so A goes to twice B. So this is very simple that if you have 1 mole of A, then it will lead to 2 moles of B, and then you have this stoichiometry. Okay, so this is an experimentally derived fact that you have this stoichiometry. But you can, this stoichiometry should also follow according to the reaction mechanism. That is what we are trying to emphasize. This stoichiometry should also follow according to the reaction mechanism, and the reaction is divided into steps. All right. So we will talk about elementary reactions and other things. So this particular reaction, like this NO catalyzed oxidation of SO2, by these two steps. So you have first the oxidation of NO itself to nitrogen dioxide, and then sulfur dioxide reacts with this intermediate nitrogen dioxide to give you sulfur trioxide and nitric oxide recovered. So nitric oxide is kind of a catalyst over here, right? Because it is regenerating at the end of the step. And you can so basically you have this kind of situation where you can also have it in the, because it is appearing in the reaction itself, therefore it is being taken into the account of the it is coming into the rate law as well. Okay, it is coming into the rate law as well. Then there is the example of this N2O5. This is another example that we talked about in the previous class, and the rate law over here was R is equal to N2O5. I think it is first order. Yes, this is first order. All right. So this is another, and this is also a multi-step reaction. This is also a multi-step reaction. Now, what you see over here, typically in the first case over here, that the steps must add up to give the stoichiometry. The steps must add up to give the reaction stoichiometry. So the mechanism steps must add up to give the reaction stoichiometry. That is why you have multiplied it by 2 and all that, and you have finally added up the whole thing to get the reaction stoichiometry, that twice SO2 plus O2 gives twice SO3. This particular stoichiometry is recovered, which is the experimental stoichiometry, through if you postulate this mechanism. But this mechanism also must have the support of other experimental evidence. For instance, the appearance of the intermediate, right, the NO2, etc. And besides that, you also need to have the, that is ultimately it must agree with the experimental rate law. That is, the predicted rate law from this particular reaction mechanism must be in accordance with the experimental rate law. If all these things are coming together, then you may say that the mechanism is correct. Okay, may say, that is because even this set of evidences could be true for another similar mechanism as well. That is why I'm saying may say. So there have been evidences in history that a particular mechanism which was well established for many years was disproved at a later stage because of new evidence that had come up, new experimental techniques that had come up, new analytical techniques that had come up. Okay, similarly, this particular reaction, the decomposition of N2O5, nitrogen pentoxide, this is also a multi-step process, and again, these are the steps in the mechanism. These are the steps in the mechanism A, B, C, and you add up the steps in the mechanism and you get the ultimate, the stoichiometric equation. So these are the stoichiometric, and you can see always that there is no relation between the stoichiometric equation and the rate law. There is no relation. There is no relation between the stoichiometric equation and the rate law. So that is extremely important to remember. Don't get confused. Okay. Right. Now we come to the, so each step, now we come to the definitions based on this example, that each step in the mechanism of a reaction is called an elementary step. You don't call it an elementary reaction, actually you call it an elementary step. So I would prefer the term elementary step. All right. Then, but you can also have an elementary reaction. You can also have an elementary reaction. What does that mean? It means that the reaction has only one step. The reaction has only one step, and therefore that simple elementary step is that elementary reaction itself. So if a reaction has only one step, it consists of a single elementary step, then it is an elementary reaction. Then only it is an elementary reaction. I think you have been taught about elementary reaction, or it has been mentioned in the class 12 book as well, if I remember correctly. All
Yes,
right.
sir.
Yeah.
Yes,
So
sir.
Yes, sir.
and if you anything more than an elementary step, that if the reaction has more than one elementary step, okay, if a reaction has more than one elementary step, then it is called a complex or composite reaction. All right. These terms are actually used, different books use different terms, but generally it simply means that the reaction consists of mechanism steps, more than one mechanism step. Okay, so two or more elementary steps, then you say it is a complex or composite reaction. So for instance, here N2O5 decomposition is complex. So most reactions are composite, of course, most reactions. Okay, very few reactions in fact are simple elementary reactions. That is, one step reaction is a rarity. It is a rarity. All right. Then we come to another important, that number of times you saw in the previous slide that a particular mechanism, all right, a particular step in the mechanism, occurs a number of times. That is, you are multiplying that step by 2. Remember here, you are multiplying this step by 2, and so here also 2, like that. So the number of times a given step in the mechanism occurs for each occurrence of an overall reaction is known as the stoichiometric step. So you have to talk about the stoichiometric number S of the step, how many times it is occurring. It is not important. It is not important. It is just a way to describe what is happening. This particular sentence is not important. Okay. But the next sentence is very important. The next sentence is very important. Now we define what is molecularity, because there is a lot of confusion among the students about molecularity. What is the concept of molecularity? Molecularity you can define for only for an elementary step. You can define molecularity only for an elementary step or an elementary reaction. If you are asked about the molecularity of a reaction, then you can talk about the molecularity only if and only if it is an elementary reaction, not otherwise. For a composite reaction, there is no concept of molecularity. There is no concept of molecularity. Okay. But you can always talk about the molecularity of an elementary step. That is, in one step of that mechanism, how many reactant, atoms, molecules, etc. radicals are involved in the step. So you can talk about the step. So what is molecularity? Molecularity is the number of molecules or reactants which are involved in an elementary step or elementary reaction. Okay. If it is one step reaction, then it is elementary reaction. All right. So you can talk about an elementary reaction molecularity, but not otherwise. Nothing else than that. So for in general, for a reaction, because if you do not know whether the reaction is composite or whether the reaction is elementary or not, if you don't have that knowledge, then you should not talk about the molecularity. All right. Molecularity is a
Sir,
concept which comes from, yeah, someone wants to ask a question.
sir, previously we defined molecularity for the complex reactions also, in which we find the molecularity of the rate determining step. So what does it mean in that step? Why we define there?
I said molecularity, you cannot, number one, first of all, you cannot talk about the molecularity of a complex or a composite reaction. Is it clear? Okay.
Yes, sir.
Yes, sir.
The second thing is, you said molecularity of the rate determining step, right? So when you say molecularity of the rate determining step, you are talking about an elementary step. You are talking about an elementary step in the mechanism. All right. So you can talk about the molecularity of an elementary step in the mechanism. So you can talk only about the elementary step. What are these? These steps are elementary steps. These are elementary steps. That is what I wanted to emphasize. This is a multi-step mechanism, but these are elementary steps. All right. For each elementary step, you can talk about a molecularity, but not otherwise. You cannot talk about the molecularity of the whole reaction. And remember, the elementary step is according to a postulated mechanism. Experimental reality is only the rate law and the stoichiometric equation. Besides that, everything else, that is the mechanism, etc., lives in the theoretical space, right? It lives in the theoretical space. Okay, so we can only define molecularity for an elementary step or an elementary reaction. All right. So that is what we conclude with this discussion. I hope I have explained this concept. Okay. All right. So now the rate law, of course, you can, for an elementary step, you can write the rate law directly. If you know the elementary step, you do not know the elementary step from elementary step is something which is theoretically or which is coming from evidences indirect, and you are just proposing. It is a proposal. It is a postulate, right? So this we explained earlier as well, that the mechanism, how does the mechanism come about in the previous class. All right, now we come to integrated rate laws. This is something again which you have seen earlier as well. So we will be moving across. So this is the integration of rate law. Now the thing is that you want to have it in an integrated form so that you can plot it. So this is, first of all, this is the general scheme of things, that if the rate is directly proportional to a raised to the power n, that is a is the reactant and raised to the power n is the order, okay, and n is equal to 1, then it is first order, n is equal to 0, then it is 0 order, likewise. So n is equal to 0, that is 0 order, and n is equal to 1 is first order. So all these things you know.
Sir?
Yes.
Sir, nu A and nu B are the stoichiometric coefficients, so how nu A can be negative?
Nu A can be negative. Nu A is negative by convention. We are putting in a convention. And why do we put that convention? That also I mentioned in the previous class. We put in the convention because this derivative is negative. If you think of it carefully, what is this derivative?
Negative.
A is decreasing, T is increasing, right?
Yes, sir.
Right or wrong?
Yes, sir.
Yes,
Right?
sir.
So smaller
So
value
for
minus
the
larger value.
reactant stoichiometric coefficient, you keep it negative, and the product stoichiometric coefficient, you keep it positive.
Positive.
Yes, sir.
Okay. So this is a simple integration that we have shown over here, and I think this you have already done your 12th level, so I do not need to repeat it. That if it is a zero order reaction and you have the limits, A0 is the initial amount of that reactant A, and A is the final amount that is remaining after time t, then you can integrate it and the integrated expression looks like this, right? Now, of course, the whatever I have written over here in pen is something that I have mentioned in the earlier class, that if you do not take into account the stoichiometric coefficient, like here, twice A gives B, then the rate equation rate will look like this: 1 divided by 2 minus dA by dt is equal to K, and you can then integrate it. But if you take the 2 over here and then you talk about this, then this can be explained as Ka, and hence Ka, that is the rate constant for the consumption of A, has this relation with the true rate constant K, the true rate constant K. So we are talking about two terms: Ka, the rate constant for the consumption of A, and K, the rate constant for the reaction itself. Okay, and there is a relation between the two.
Yes, sir.
Okay, so if we go to first order reaction, again the expression is pretty simple. Then we integrate it with A as the upper limit and A0, that is the initial amount of the reactant, as the lower limit, and T is the final time T, and 0 is the initial time. The reaction, you have just mixed up the initial reactants. So if you do that, then you get this ln A by A0 and you get this expression. You can write it in the exponential form as well. So this is written over here. Now, if you want to write it in terms of B, that is the product form, that is also possible, of course. That is, if you are talking about this reaction, A goes to B, right? So if you want to write it in this format, then it is A0 is the initial amount, and whatever A0 is, that will be converted into that at time T will be A plus B. B is the product, A is the remaining reactant. So at time T, at any time T, it will always follow this mass balance equation. This is the mass balance equation. So you can plug it, this A0 minus A, and you can get this expression, right? So this is another expression if you want to talk in terms of B, all right? And then you can also write down the expression for the second order reaction. It is also very simple. So you get this second order reaction, then you integrate it and you get this. Now let us go to the next slide, because this slide has. Now we come to something which you have not seen. You have seen those mathematical expressions before and you have worked out a lot of problems with them. So I did not spend any much time with that. It was something that you have done a lot. Now let us come to some practical aspects. For instance, let us take up an example. This example is the hydrolysis. It is in fact the acidic hydrolysis. The acidic hydrolysis of triphenyl methyl chloride. Okay, it is the acidic hydrolysis of triphenyl methyl chloride. And this reaction exhibits first order kinetics. What do we mean by that? What do we mean by that? And how do we track it? What do we mean by that? That is number one. And how do we track it? How do we do the experiment actually? All right. We will come to the details as well, that in your lab class it is given. But let us see here in brief. In brief over here, we see that for each hydrolysis of this particular molecule, triphenyl methyl chloride, you are generating some acid, right? In a stoichiometric manner. So if you can measure the acid generated, rather the rate of acid generation, okay, rate of acid generation, if you can find out, then you can use it to plot the kinetics. Use it to plot the kinetics. Okay. So what do you have to do? You have to measure the amount of acid, or you can also do a pH metric titration, that how is the pH changing with time. How is the pH changing with time? That is another way of tracking the acidity of the the acid concentration of this particular reaction. Okay. So you can see these graphs that we plot over here. This is triphenyl methyl chloride and the acid concentration. All right. So one the graph that is coming down, is for triphenyl methyl chloride, and the graph that is going up is for the acid concentration. Now you can see over here as well, this is a log plot. This is a log plot, and therefore it is giving a first order log relation. And likewise, the third is normalized by some quantity. So I'm not going to, this is also a logarithmic plot, but I'm not going to discuss that. Anyway, so this is the way we track a particular reaction. And how do we look at the if it follows a particular equation, integrated rate law, then we can say that it is first order kinetics or second order kinetics. For the second order kinetics, this is another example of second order kinetics. So if it is following this inverse kind of relation here, this one, that is A raised to the power -1, that is inverse relationship, and it is giving a perfectly linear graph, then it is a second order situation, right? But if you try to do a log A kind of graph, then you will see that it becomes non-linear. It becomes non-linear because this is not a first order kinetics. This is not first order kinetics. It's not following first order kinetics. Okay. Right. So here we come to the simple. We have in this table we have summarized some of the expressions, very simple expressions. A goes to B kind of expressions for zero order, first order, and second order. What we have added in this table, is after writing the integral form, we have also found out the half-life expressions. So you can see that for zero order, if it is zero order, then the half-life expression T half is proportional to the initial concentration A0. So you can actually plot different initial concentrations. You can do reactions with different initial concentrations of the same substance and then plot it against the T halves, and thereby if it follows a directly proportional kind of this graph, then it is a zero order kinetics, right? For first order, this is another very famous expression that you people have used in lots of numericals. T half is not proportional on, it does not depend on initial concentration. T half does not depend on initial concentration or any concentration of A. So T half is actually dependent only on the rate constant, right? And second order, T half is actually inversely proportional to the initial concentration. So we will see later on, that how we can use this half-life of a particular reaction to also find the rate laws. Half-life method is also a method for finding the order of a reaction. Okay. Before we come to that, that is how to find the order of a reaction, let us do some more very simple, not very complicated, simple integrations. Okay. So let us consider this reaction. A plus B gives P. All right. And the additional constraint that we are putting in is that the initial concentrations of A and B are not the same. That is, A0 is not equal to B0. A0 is not equal to B0. So we can write down the following mass balance equation. That is, A minus A0 is equal to B minus B0 at any time of the reaction. At any time of the reaction. And hence you can also write A minus B is equal to A0 minus B0. Okay. Now we can write down the rate of the reaction.
Hello, sir.
Yes.
Sir, can you please explain the mass balance equation, that how it is arrived at?
Which mass balance equation? Okay, the previous one. Okay.
Yeah,
So
A minus A naught one.
A minus A0. All right. So what is the problem with this? If you have, that is, whatever the difference between A and A0, that will be the difference between B and B0. A0 is the initial concentration of reactant A. A is at time t, right?
Yeah.
So whatever the difference between the two, that is has been converted into product.
Yeah, okay. I got that.
Okay, so so we have this dA by dt, and now we can write down this particular expression. Now look here, whatever integration we are doing, we are always assuming that the reaction is elementary. Remember that, because unless you assume that the reaction is elementary, you cannot do this. You have to assume, when you write this kind of thing, A plus B gives P, and then you write this rate law, then you are basically saying that this goes in one step. This goes in one step. There is no hidden step over there, and hence it is an elementary step. Therefore, you can write dA by dt is equal to K A raised to the power this 1 and B raised to the power 1, right? And similarly for B and T, this derivative, the second derivative for the second reactant B. Okay. Now, therefore, you have two rate equations now, because dA by dt and dB by dt. So you have two rate equations. You can write down the two rate equations separately, and in the second step, you can write it down like this. So you can do it like this, and then you can subtract the two here in the third step. So you have subtracted the 2 in the third step, right? And finally you use the mass balance. This A minus B is equal to A0 minus B0, A0 minus B0. Invert it and get the answer. Then integrate it and get the answer. Okay. Again, the limits are of course A and A0. A0 is the initial concentration, A is the final concentration at time t. B and B0. B0 is the initial concentration, B is the final concentration, right? So you got this equation, this expression. There is another way of getting the same expression. So alternatively, we can also use the method of partial fractions. So now we write that when A has fallen to A0 minus X, B also has fallen to B0 minus X, right? So hence we can write down dA by dt is equal to this particular rate law, right? A0 minus X into B0 minus X. So because this A0 minus X, if we take the derivative, then it is equal to dx by dt minus dx by dt, of course. And then you can write down dx by dt K A0 minus X B0 minus X. So again, if you do it for integrating for the limits, that is x is equal to x, x is equal to 0, at time t is equal to 0, time t is equal to t. Then you integrate and use the method of partial fractions to integrate. Then you get the same expression as earlier, right? You get the same expression as earlier. So both methods of integration can be used. This is something which you are more familiar with. That is why I included it. Sometimes the students say that they are not familiar with the earlier one. But that is an easier way. But anyway, this is also a well-established way, method of partial fractions, right? Okay. So now we come to, now we have done with the integrated rate laws, the expressions that we are going to use in this case, in this particular course. We have already gone through those integrated rate law expressions. Okay, we will not go for very complicated integrated rate law expressions. There are actually, if you go to books, etc., then you will find there are many more derivations of many more integrated rate law, maybe third order rate laws, etc., and all that. Not simple ones, but if you have two reactants and all these kinds of things, different kinds of permutations. But let us not go for that. Let us go for more principles instead of mathematics. We are trying to understand chemistry rather than mathematics. Mathematics is over here. Mathematics is only a tool, not the idea, not the objective. Right. So let us concentrate on what are the methods for determination of the order of the reaction. By order of the reaction, we mean that the first target is to find the partial orders. That is, if you are talking about A plus B gives P, then you want to know what is the rate law in this format. That is, what is X, what is Y, what is X and what is Y. If you can write the rate law in this format, if you can write that, that is also another question that we have already addressed. But supposing if you can write the rate law in this way, then what is X and what is Y? If you know X, that is the partial order. If you know Y, partial order with respect to B, then you can add the two. X plus Y is equal to N, right? So this is the objective of this particular section of studies. One particular approach for dealing with this kind of problem is the isolation method. Okay, is the isolation method. The isolation method, first of all, we must understand, is not a method or is not a technique for determination of order with respect to a reaction. It is not. It cannot directly tell you what is the order with respect to a reactant. It cannot. But it can simplify the problem. It can simplify the problem. Okay. So what it does is it reduces the rate expression which you have written like this here. This particular rate expression. Okay. Suppose you have written this particular expression. So it can reduce this rate expression to this expression. Okay, it can reduce it to this expression, or it can reduce it to this kind of expression. All right. So this is the idea. Now you have only one reactant. If you can reduce a multi-reactant situation to one reactant situation, or in the rate law, there are many reactants to be taken care of. You have to find out the order with respect to every reactant, and instead of that, if you can find out the order of a reactant partial order of a reactant at only one, that is one at a time. If you can do it one at a time, then it becomes very simple, because the integrated rate laws are simple for this kind of situation, right? The integrated rate laws are simple for this kind of situation. You can also use the half-life kind of situation. You can also use the integrated rate law kind of expressions to find out the order of the reaction, order with respect to A, order with respect to B, and then you can add the two to find the order with respect to the whole reaction, order of the whole reaction. So what are we doing? How do we do it? How do we do it? We induce what is called a pseudo order. For instance, this example, let us take this example of hydrolysis of sugar. Okay, this is sucrose, water. There is actually acidic hydrolysis, so it is acidic hydrolysis. The acid is not written over here, but it is there. 1 minute. So you can write over here H plus. Okay, acidic hydrolysis. This gives you glucose plus fructose. Okay, so this is a hydrolysis reaction. Now over here, water, H2O, is the solvent, but it is also a reactant actually. When you talk about the solvent, you should not be very sure, like hydrolysis. In hydrolysis, water is always a reactant, right? Hydrolysis means cleavage of the water molecule to do a reaction. So hydrolysis, water is always a reactant. So if it is a reactant, then it will be a part of the rate law. It will be a part of the rate law. But because H2O is always present in great excess, therefore, relative to sucrose, relative to the concentration of sucrose, so there may be a small change in the concentration of sucrose. Whatever the change in concentration of sucrose, the change in concentration of H2O is negligible. The change in concentration of H2O is negligible because it is the solvent itself. Right? Because it is a solvent itself. So H2O is present in great excess, and what is present in much lesser concentration, that is sucrose, you just track that, because the other one is not possible to track because the change in concentration is very, very small over there. So you can always neglect it. Likewise for H plus as well. Acid concentration is also over here much more in excess. So the correct rate law, if you want to know, it is this for this particular expression. This H2O raised to the power 6, H2O, and this. But instead of that, you get access to this pseudo rate law. This is called the pseudo, the highlighted in blue. It is called the pseudo rate law. Obviously, this K, this particular, sorry, this is not, I can. This K is not the same as this K. Okay, this is again, need to change the color. This K is not the same as this K. That is why I have also written over here K app prime. Okay, and this is K app only, because what is happening, that when you are doing a pseudo order kind of situation, you want to do this isolation method. What do? You always take one reactant in great excess and the other reactant in normal concentration. Take one reactant in great excess Okay, so if you do that, then the concentration of that particular reactant is not changing. Suppose B is in great excess. Okay, then you have because b is in great excess, so b raised to the power y, this whole expression becomes a constant. This whole expression becomes a constant because it is in great excess. So you can write therefore k app, because now the k app includes k b raised to the power y. K b raised to the power y, that includes it, and a raised to the power x. So you can write it like this, okay? And so this is a pseudo approach, that is pseudo order kind of approach. That is what we say, that if it is say x is equal to 1, then we say this is pseudo first order. We say pseudo first order because the other reactant order we have not determined as yet, but it is order with respect to this particular reactant which is not in excess. So we call it pseudo order of this particular reaction. But if we have the other guy as constant, say A is the excess, large excess, then obviously the K app will be K A raised to the power X, and obviously this K app will be different from the other K app. This K app will be different from the other K app. So this K app is different from the earlier K app, right? K app prime.
Sir?
That is why we write K app prime. Yes, someone has a question?
Sir, in the example given by you, a plus b gives rise to p. Can we say that that k is equals to k apparent into k apparent prime?
Can you say it again? I did not hear you properly.
Sir, in the overall rate expression, rate is equal to k into a power x into b power y. In that
Yes.
case, there no sir.
Yes.
In that expression, k is equal to. Can we write like that?
No. So okay. So whatever you want to say, you can write it down and send it to me. All right, in the chat box. So I will reply. All right, because right now I'm not able to get what you are saying. All right. Hmm. The mic is not properly working. I think the sound is breaking. When you are saying something to me, the sound is breaking a bit. So I'm losing a few words here and there. All right. So now this is, we said that this is the way, that is the isolation method. This is also known as the flooding method. Okay, isolation or flooding method. Let me write it. So this is isolation or flooding. That is, you are flooding the situation with one reactant. There is a flood of one reactant. Okay, so flooding, isolation or flooding. This is to simplify the rate law expression. Okay, this is only to simplify the rate law expression. But then once you have got this pseudo rate law, you still have to find out the order with respect to A or order with respect to B, right? You still have to find out the order with respect to A or order with respect to B. So how do you do that? That is the next question. So one technique, very simple, is of course to use the integrated rate law, because now we have simplified the rate law to a pseudo rate law where there is only one term, right? So we can use the simple integrated rate law expressions that we have found earlier, that we derived earlier, right? So that is one way. But there is a problem, and this is something that we will discuss in detail in the next class, because it is already 8:55. I think your class is only up to 8:55.
Yes, sir.
Yes, so the integrated rate laws are assuming and deriving rate laws based on, say, zero order, first order, second order. But there is always a possibility of getting a fractional order. This we have seen in a rate law expression earlier. So how do we deal with that? All right. A priori, we do not know whether the rate law will be fractional or integral or something. We just don't know, right? So we will talk about this in the next class. So with that, I will end the class. You can post the.
Sir, will you upload the slides?
Yes, I will upload the
Sir, will you
slides.
upload the slide?
The recording